Hey, welcome back to Fat Mama Physics. This is part 2 of 6.4 similar triangles. We are going to look at some real-life applications of similar triangles. I have a video that when I was in Italy, Florence, I went into this museum called Museo Galileo. They have a really cool app, which is on my phone. It's actually free, even if you don't visit the museum. And here, I'll write it out. It's called Museo Galileo, which if you're familiar with Galileo as a scientist who pretty much he was the target of the church because he found that the earth is no longer the center of the universe, because back then they thought that the sun orbits the earth, but it's actually the other. He found that it was the other way around, and it caused a big uproar in the church. He was under house arrest, and he was a guy, and later on he discovered so many amazing things before and afterwards. Fantastic, very interesting part of history. So this museum features a lot of what he did, but also a lot of instruments of war, a lot for military instruments, and the one I have is a surveying instrument. They need to survey the land in order for, say, for military purposes, for drawing maps, and they use similar triangles, proportions to do that. So here I have part of the video I'm going to show. I have to cut it out if I can't, if they're not allowed on YouTube. So let's do this right now. Here we go. So you see in front of you, this is called Lanci's, I forgot his first name, Lanci is Italian, Lanci's surveying instrument. So I'll play part of it. I'm not going to play the whole thing. Okay, so you have these rotating arms that can move freely about. So take a look here.
A topographic survey can be made by triangulating from two stations where the distance between them is known. Let us consider the surveying of a course of a river from a hilltop. The instrument is positioned at the first station and its sliding bar aligned with the second. We know that the distance between these two station points will be proportional to the distance between the two folding arms on the sliding bar. The surveyor, standing at the first station, sights a point on the river's bank through the sighting device on the arm at the left end of the sliding bar. This arm is blocked before moving the instrument to the second station. From this new station, the surveyor aligns the sliding bar with the first station and sights the same point on the bank through the sighting device on the right arm. The triangle formed by the arms and the sliding bar will be proportional to the imaginary triangle whose base is the distance between the two stations and whose vertex is the point on the bank. The surveyor thus obtains a direct representation in scale of the landscape's topographic features. The distance of this point from the station may be measured on the basis of the two similar triangles formed. All other significant points may be measured from the two stations.
That's a bad drawing. Oh well.
If a drawing sheet is placed on the disc,
Okay, so you kind of get an idea how they used similar triangles back then to survey the land, to find measurements, etc. So, so essentially, one part he didn't quite say clearly, which kind of got me when he first talked about it, was the fact that you had to take that surveying instrument from point A to point B. It's not like you have a separate instrument. So you keep the shape of the horizontal bars, and once you put it at point B, you just have to make sure that the bases of the triangles are aligned on the bottom from A to B, and then you take the other slider for the other triangle to make your similar triangle there. So very interesting stuff. Okay, let's come back to here, and we use similar triangles to measure anything, not only horizontally but also vertically, using very similar idea here. So example 3 here, let me give you some context, and maybe if you want to solve this problem later by yourself, you can. Here we have a person standing versus a totem pole, And at a certain time during the day where the sun, let's say, is over here, it's gonna shine rays, and and the rays are relatively going to be pretty much parallel to these two lines because the sun's very far away. If the sun's very close up, that's different because the sun rays are. Anyways, less about that, more about the actual question. So you have two parallel rays coming down, meaning that with a certain amount of height, you're going to get a proportional base that relative to one another, you can find a scale factor too, because this angle here in this triangle is going to be the same since you have two parallel lines. Okay. So here's the question. At a certain time of day, a person is 1.8 meters tall, has a shadow of 1.3 meters. At the same time, the shadow of a totem pole is 6 meters long. So that's a shadow here. And the sun's rays intersect the ground at equal angles. Okay, so they talked about how these triangles, this angle here is the same. But I just kind of talked about from a science perspective how these two angles are also the same because the rays from the sun will be parallel to one another if we are talking about a faraway distance. Okay, so here we have the similar triangles. We use sun's ray to shadows, form two triangles. If we can show the triangles are similar, we can use a proportion to determine the height of the totem pole. Assume the totem pole and the person are perpendicular to the ground. Oh, hey! So now we also know another angle that is similar, another angle that's the same, and as well as the top, their angle being the same as well. So now we have two triangles. And why we like to do this? Because we can physically measure this distance on the ground, same as this shadow on the ground by the totem pole and person. We know the height of the person, but if we had to measure the height of the totem pole, we had to get a ladder, we had to get a helicopter, whatever it is, and we got to use that to determine the height. Whereas we can just use a bit of math to do a bit of proportions to figure out the height. A lot easier, right? So now you have two similar triangles. Maybe it'd be a good time for you to pause the video and try to figure out the height of the totem pole. Good time to pause the video. Okay, now I am going to solve this one together. So we're going to do the idea of similar triangles in which we know both the shadows are going to be proportional. So since I want to figure out this height here, I'll call it x, okay? And I want x to be, I know the ratio of the height to the shadow is going to be this. And I want to make sure that the ratio of the height to the shadow is going to be the same as the person's height to the person's shadow, which is 1.8 meters over 1.3 meters. And now what I want to do is I want to figure out what x is by multiplying both sides by the 6 meters. Whoopsies, that doesn't cancel. This one over here cancels. So I get 1.8 over 1.3. This is then multiplied by 6. I get 8.30, 8.30 ... or this is about 8 meters tall. Actually, 0.3 is not bad. 8.3 meters tall, okay? So now we have a similar situation below where I have two overlapping triangles. So a surveyor, hey, this is kind of like what we were talking before in that first video we showed you, if we did. Assuming YouTube didn't cut it out for me. Using overlapping similar triangles to determine the length. So good for surveying the land, especially if you don't want to take a meter stick and measure it, or measuring tape. So here, we want to determine the width of a lake at 2 points on opposite sides of the side of the lake. So that's going to be H and N. She measures the distance and angles on land and sketches a diagram. Find the length of HN. So we want to find out this side here. And let's say this was something that we could physically measure, so that it'd be a lot easier to do to figure out the length of the lake. We need to identify the two triangles. We need to figure out which sides are proportional, and that's usually the part where it's tricky. We know for that both triangles, and you might be thinking, where's the other triangle? So first here, this is the first triangle here. The smaller one, this is the triangle that the person is able to measure. It's easy to do. The one that is harder is the one that is starting from here but goes all the way back. There you go. Okay, so that's the second triangle. It's going to be very similar to the first triangle. And hey, doesn't this kind of look like the pyramid example that I showed you in the board game in the first video? In which this angle is going to be the same for both triangles. And the other side here, this is going to be the same here. And this one is going to be the same here. And take a look. It looks like these two lines are parallel, which should be the case in order for this triangle to be similar. So we have identified the two triangles. We need to find the corresponding angles. We just did that too. Next up, we want to find the corresponding sides. Then write a proportion that includes the unknown length. Okay, so guess what? I'm going to give you a chance to try this question out. At the end of the day, you want to find the width of the lake, which is HN. So good time to pause the video. So we want to find the unknown length. The unknown length that we're interested here is the length of HN, which is the lake. Okay. Now, in order to find the length of that lake, we need to find the corresponding side of the smaller triangle, in which it's going to be this one. So these two are corresponding lengths. We know the smaller corresponding length to the smaller triangle. So we need the scale factor in order to find the entire length of the lake. So to find the scale factor, we need to use another part of another corresponding pair of sides on the two triangles in order for us to find the scale factor. And that's going to be this one here. It's going to be this side for the smaller triangle, and then it's going to be this entire length for the bigger triangle. If we have to write a ratio for these two sides to in order for us to figure out the width of the lake, it will look like this. So the lake is going to be the one we're interested. So that's HN. That's side HN. Divided by the smaller side, which is PQ. So that ratio is going to be exactly the same as the ratio of this entire long length of this bigger triangle, which is HJ, over this smaller side of the smaller triangle, PJ, pajamas. So that's the ratio here. Big to small is going to be equal to big to small. Okay, the ratio is going to be similar. So if we substitute in some values, we're going to get HN as, we still don't know what HN is. We'll find that out. But this is over PQ, which is 230 meters, which is this smaller side base of this triangle. And that's going to be equal to this side of the triangle, in which the longer side, HJ, is all the way from here to there. That's 305 meters plus 210 meters combined. Not just this, just be careful, you have to add the two sides together to get your entire length of the side of the triangle. And that's going to be over PJ, which is just from here to there. That's just 210 meters. So if I wanted to, I can simplify this one. And that's going to look like, whoops, no, not what I want to do. That's going to look like HN is over 230 meters. 305 plus 210 is going to be 515. 515 meters over 210 meters. Okay, now we just have to solve for HN. Okay, so to solve for HN, I'm going to multiply the 230 up on both sides like this. Okay, and that's going to get rid of that, in which I have remaining HN is going to be 515 meters times 230 meters. All of that divided by 210 meters. So let's put that into the calculator. What is that going to give us? That is going to give us 564. And there it is, 564 meters. And seems like rounding up to the meters is going to be sufficient. Okay, because that's, okay, so that's it. All right, so Key thing about these triangles is to make sure you identify the corresponding sides, otherwise it'll be difficult to figure out your scale factor, your ratios, to calculate your missing side. So, hopefully you learned something from these videos. I wish you good luck, and Fat Mama Physics signing out!